okay, onto the subspace U, this is an element in U pi. This is also evident from the definition of the orthogonal projection actually. Okay, and say for example, another part F is really that the norm of the orthogonal projection, okay, the norm of the orthogonal projection of the vector V onto the subspace U is less than or equal to the norm of U actually, okay. So this also shows that under the orthogonal projection, sizes are not preserved actually, okay. The sizes are not preserved, not necessarily preserved. Could be preserved, you can have equality. In other words, a projection can be an isometry, but it's not necessary that this should always be equal. So let's see that why some of these things are true. So the first is really to take, for example, two vectors and orthogonally project. So take, for example, two vectors U and project them onto. So in other words, take the linear combination of two vectors AV1 plus VV2 and project them on the orthogonal subspace, what do you call V. And let's see that why this is equal to what do you call the other result actually. Okay. So if I assume, okay, I may assume it here that U1, U2, UR is orthonormal basis of the projection space U actually. So this would be equal to the sum that goes from I equal to 1 to what do you call R, the vector AV1 plus VV2, its inner product with UI multiplied with UI. This is what the definition of the orthogonal projection of a vector is. Okay. So you can simplify this. So I can break this inner product out and I can have I equal to 1 to say R, and I can say that let's take A out and you get V1 UI, UI. So even if I wish, I can even take this out, A outside of the sum plus I can do the same B I equal to 1 to R and the vector V2 UI and the inner product with the UI. And this is same as you have A times the orthogonal projection of V1 onto U plus B times the orthogonal projection of vector V2 onto U, and this shows that B is linear. What would be the part B? The part B is going to be that, okay, take a vector V from the space V, okay, and project it onto the subspace U actually. So by definition, you're going to get this. So what is the basis of this subspace 0 actually? The basis of the subspace 0 is really, what do you call the subspace 0 actually? Okay, so it's subspace 0. So it's going to be the 0 vector itself. So I'll take this V, take its inner product with 0 and multiply this with 0. So you're going to get the vector 0. And I can treat this as that the 0 transformation operated onto the vector 0. And what does this shows? That, 0 transformation operated onto V. So what does this show? That the orthogonal projection of vector V onto the vector 0 is equal to the 0 of V, and this is true for all V in the inner product space V, so therefore this must be true. Okay? So think about this for yourself. Range of PU is U. This is also evident actually. Okay, this is true from definition, that if you take, for example, PU and operate it onto the vector V, then this is equal to what do you call a sum that is I equal to 1 to R, I equal to 1 to R, V, UI and UI, where UIs are the bases of the subspace what you call capital U. So this is really one of the linear combination, okay, of the bases of the space what you call U. So this must be an element in U. This must be an element in U actually. So this shows that this must belong to the element in U. And if you take, for example, any vector from U, it also belongs to what do you call, again, it belongs to the range of PUV actually. So this really shows, what does this shows? This shows that the range of, okay, so I must write this explicitly, okay, the range, the outputs of this map belongs to the space U. So the range is subspace, and you can also see that U is also subspace of the range. So this is evident from the definition actually. Why the kernel of U must be U perp? Okay, so let's see this, that if you consider the kernel of the orthogonal projection, by the way, this result is true in infinite dimension as well, because there is no restriction on V actually. V could be infinite dimensional as well actually. Okay, so the kernel of this map PU is going to be the collection of the vectors from the V for which the PU of V is PU operated onto V is equal to 0. Okay, this is what is really the case. Now if you simplify this a bit more, so the V operated onto the space V, and this is sum that goes from I equal to 1 to n, okay, and projection of, so this is going to be V times UI, okay, times UI equal to 0. Okay, so this is a 0 vector. So if this is a 0 vector, UIs are non-zero. So this means that these what do you call, these coefficients are 0. So the coefficients are 0. So V from U, so it's going to be that these coefficients V UI equal to 0 for all I equal to 1, 2 and up to R. And what does this show? This shows that V is orthogonal to the bases of the subspace U actually. So if it is orthogonal to the basis of subspace U, then it is orthogonal to the all vectors in U for sure, because all vectors are linear combination of the bases. So if they are orthogonal to bases, that means they are also orthogonal to all linear combinations actually. So what does this show? That V belongs to the U perp. Okay? So this shows that this kernel of PU is really U perp. Okay? So I hope this makes sense to you. This is also trivial actually. This is also trivial. So we previously said that, okay, every V can be written as U plus V minus U. And actually U is this, where this U is from the U, and this V minus U is from the U perp actually. And this U is basically the orthogonal projection. Okay, this is the orthogonal. From this representation you can write another thing, that every V is the orthogonal projection, okay, of V onto the subspace U plus V minus the orthogonal projection of V onto the, what you call U. And we know about this, that this belongs to the U perp. Okay, so this means that V minus the orthogonal projection of V onto U belongs to the U perp. So this is really evident actually. Okay, now really the last part is, so this is basic. Okay, it's not difficult. You can check it for yourself. Now really the last thing is to think about the f actually. That the part f, which says that the orthogonal projection of the vector v onto the subspace is less than or equal to the norm of v. Okay, norm of v. Now, if if I say that the orthogonal projection of u onto v is a vector u, then we know that this vector u belongs to u actually. And v minus this vector u belongs to u par. So this is known to me. Okay. So I can now say that the orthogonal projection of, say, pu operated onto v is equal to the norm of u. Okay, is equal to the norm of u, and this vector u can be written as the vector v minus u. Okay, so I can write this as or I can say that this is less than or equal to norm, or maybe if I talk about the square of it, this is better. So this is less than or equal to norm of u square plus norm of v minus u square actually. Why? Because this is a non-negative quantity which I have added into it, so this must be bigger than or equal to this. Now these two vectors are orthogonal, so by Pythagorean theorem I can say that this is equal to u plus v minus u vector square. Okay? So by Pythagorean theorem, in inner product spaces you have this result. And once you have this result, this shows that this is exactly equal to the norm of v square. So this shows that the orthogonal projection of the vector v, or the norm of the orthogonal projection of the vector v onto the subspace u is less than or equal to the norm of the projected vector actually v. Okay? So this really completes the result. Okay, this really completes the proof of the result. So I hope this made a little bit of sense to you. So now let's get to some more properties of orthogonal projections. So we saw some properties of orthogonal projections. So let's get to the more properties of the orthogonal projection operator actually. So now we're going to focus on the operator properties of the orthogonal projection operator. Okay? So here's the theorem which says that if u is a finite dimensional, okay, so this is a finite dimensional subspace of the inner product space V, then following is true. The projection operator of the perp space, okay, the perp space. In other words, the orthogonal projection of the space V onto the U perp, okay. So if you want to calculate this operator is nothing, it's I minus the orthogonal projection onto the space U actually. So if you know this, you can easily calculate U perp actually. Okay? So you can easily calculate U perp. Just subtract the orthogonal projection PU from what you call identity operator. So this is the first property. Second property, the orthogonal projection, the composition of the orthogonal projection operator P and the orthogonal projection operator U perp, and so in other words, these two operators commute first, okay, U perp and PU, they commute. Not only commute, but they are equal to 0. So in other words, the composition of PU with U perp is 0, and the composition of the projection operator U perp with the projection operator of U is equal to 0 actually. Okay? So this is another operator. This PU operator is idempotent. So this is called that. This is idempotent actually. That is, if you compose the projection operator with itself, you're gonna get the projection operator back. In other words, you take a vector and project it onto the subspace U, and then project again that projected vector, you will return to U. So in other words, if you compute the projection operator of say U perp, okay, if you apply the projection operator of U onto the elements of U, you're gonna get the elements from the U back actually. Okay, so it's a projection operator. Projection operator is idempotent. So what is that the projection operator of U, this is interesting, is equal to, so since this is a linear operator, the adjoint operator of U perp. Okay, so no. The projection operator of U is equal to the adjoint of the projection operator. That is, this means that the projection operator is self-adjoint actually. Okay, so it's a self-adjoint operator, that because it is equal to its what do you call, adjoint. So it's a self-adjoint operator. So these are some of the things that we are interested in, for example, proving it. So there's a proof and a proof. So let's take a vector, say V, yeah, maybe just say white chalk, okay. So let's take a vector V from the space V. Then we know that I can write this V as U plus what do you call a vector W, where U is an element in U and W, which is a vector V minus U, this belongs to U perp. Okay? This belongs to U perp actually. Okay? Now let's compute the P of the U perp operated onto V. Okay, so the P of U perp operated onto V. So the P of U perp operated onto V is going to be what vector? So it is going to project it onto what do you call U perp. And what is the corresponding vector V? Okay, what is the vector that is corresponding to what do you call V in the U perp actually? So it's equal to V minus U. So this is equal to what do you call V minus U. So if it is equal to V minus U, I can say that this is same as V minus the orthogonal projection of the U onto V. Okay? Okay, we know about U, that U is, the small u is the orthogonal projection of V, the vector V onto U. So if this is the case, this shows that PU perp operated onto V and the identity operator, you know, V is equal to identity operator operated onto V, and identity operator operated onto what do you call V for all V in the space V. So therefore this operator PU perp, okay, PU perp is really equal to I minus U actually. Okay? I mean, if you are confused about this, let me remind the picture to you actually. Let me remind the picture to you. So this is my subspace U and this is my U perp. So if this is subspace U, then this is U perp. So if you have a vector V, you consider its shadow in U, it's the vector U. So if you consider its shadow onto, for example, space V, so it's going to be the vector V minus U actually. So its shadow in the space U is U, and its shadow in space U perp is V minus U. So therefore I am saying that the orthogonal projection of the vector V onto the U perp is equal to V minus U actually. So this is what really is the proof that the projection operator of U perp is I minus U. Okay? Let's move to the next part. These are the basic properties that we must always keep as it is. Okay? So let's take PU, operate it on PU, what do you call perp, and operate it on V actually. Okay? So the PU operated onto PU perp operated onto V. So it's going to be, so this is going to be the what do you say? So this is going to be the what? So this is going to be the vector. So PU operated onto V is really the V minus U. Okay, this is what it is. And this vector V minus U is going to be equal to what actually? It's going to be equal to what? So I can write this as the projection operator of U operated onto V minus the projection operator U operated onto U actually. Prove it. Why? Because we know that if you have the orthogonal projection, so the first part of, if you remember the first part of the last proposition was that if you have the orthogonal projection of the vector space onto itself, or of the inner product space onto itself, then this is really identity. In other words, that if you take the orthogonal projection of V and operate it on V, so you're going to get I of V. So if you take the orthogonal projection of the space U and operate it onto a vector which is an element of U, then this would be equal to the identity operated onto U actually. So this is really U, because the projection operator operated onto the subspace U, okay, orthogonal projection of the subspace U operated onto a vector from this space would behave like an identity operator actually, okay, from this result. Okay, so if you have a projection, if you are projecting the space onto itself, then that would be identity operator. So this is identity. So therefore U minus U is really 0. And you can do the same with PU perp PU operated onto V. So this must be really equal to 0. So verify it for yourself actually, that's why this is 0. Now let me talk about, say, D. This is also obvious, it should follow from the same fact. So if I have P square of the U operated onto, say, a vector, operated onto a vector V, why it is going to return back the element V? So this is going to be PU operated onto PU operated onto V. So PU composed with PU operated onto V. Okay, so the PU operated onto V is a vector U, and this U belongs to the space U actually. Now if you pick the element of, what do you call, this space U, and operate it or project it onto itself, onto the, the same space U, then this is identity operator, what I just wrote here actually. So this is identity operator. So this is really going to be I of u, so this must be equal to, what do you call u? What do you call u? Okay? And the u is, again I can write that this is the projection of v onto u. So p square of u operated onto v is equal to the orthogonal projection, of v onto the subspace u. So this is equal to, so they are true for all v in the space v. So if they agree onto the all v, so they are really equal, the results are. So these both operators